from Group 1. Our group will be presenting of the physical properties of element in period 3. So, I will start first with describe qualitatively in the variation of atomic radius, ionic radius, melting point, and electrical conductivity for certain elements, which is sodium, magnesium, aluminium, silicon, phosphorus, and chlorine. So I will start first with the atomic radius. What is atomic radius? Atomic radius is the distance from the center of nucleus to the edge of electron cloud. So when going across the period 3, the number of protons will increase. So the nuclear charge also increases. Therefore, the force of attraction between the nucleus and the electrons will be increased. So the atomic radius will decrease. Next, in period 3, we found that the atomic radius will be decreased at first, and then it will suddenly increase, and then it slowly decreases again. It is because in the starting element of period 3, it tends to form cation, but at the end of the elements in period 3, it tends to form anions. Next is melting point. The trend of melting points in period 3, it will increases across the period 3. It is because the strength of metallic bond also increases. So it need more energy to overcome the strong bonding. For my last part is electrical conductivity. There are 3 trends of electrical conductivity in period 3. It will increase the conductivity across the period 3, which is from the left to right, it will increases. So for the sodium, magnesium, and aluminium, it is conductor. For silicon, it is semiconductor. While for the phosphorus and the chlorine, it cannot conduct any electricity.
I'm Kushuhan from Group 1. Now, I would like to interpret the variation of period 3 elements in their melting point and electrical conductivity in terms of the presence of simple molecular, giant molecular, or metallic bonding in the elements. Sodium, magnesium, and aluminium all have metallic bonding. They have good electrical conductivity and high melting points and boiling points. Melting points and boiling points rise across these 3 metals because of the increasing numbers of electrons. The atom getting smaller and have more protons from sodium to aluminium. The nucleus of the atom getting more positively charged. The electrons also getting more closer to the nucleus. Silicon is a non-metal. It has a giant covalent structure, same as the carbon in a diamond. It has high melting points and boiling points because it needs more energy to break down the strong covalent bonds and melt it. There are no free-moving ions in silicon, so it can't conduct electricity. Silicon is a semiconductor. Phosphorus, sulfur, chlorine, and argon are simple molecular substances with only van der Waals force between them. Their melting points and boiling points are lower than the first 4 elements in period 3. Molecules prevent the electron to flow, so they cannot conduct electricity.
Next, I will continue the presentation to talk about variety in first ionization energy. In general trends, ionization energy increase across the period, but the ionization energy drop between group 2 and group 13. This is because the structure in magnesium and aluminium. In aluminium, the outer electron is located in 3p orbital rather than 3s orbital. 3p orbital contain more energy than 3s orbital. The electron is also further from the nucleus. This is causing two things. First, the increased distance between electron and nucleus, causing the ionization energy to be reduced. Second, the outer electron located in 3p orbital will be screened by 1s, 2s and 3s orbital, which will reduce the pull from the nucleus, that also causing the ionization energy to be reduced. The ionization energy also dropped in between group 15 and 16. This is because sulfur has one more proton than phosphorus. The electron that will be removed is in the same 3p shell. In the spin pairing of electron, phosphorus outer electron is removed from an unpaired electron from sulfur has one more proton than phosphorus. The electron removed is in the same 3p shell. In the spin pairing of electron, phosphorus outer electron is removed from the orbital that has unpaired electron, while sulfur outer electron is removed from orbital that has paired electron. The extra repulsion comes from the paired electron in the orbital, causing less energy for ionization energy. This is called spin pair repulsion.
Hello, Assalamualaikum and good morning everyone. My name is Muhammad Fikri Rashad. Today I'm going to explain about the strength, height, melting points and electrical insulating properties of ceramics in terms of their giant structure, magnesium oxide, aluminium oxide and silicon oxide. First, what is ceramics? Ceramics defines as rigid material that consists of an infinite tri-dimensional network of sinter crystalline grain comprising metals bound to carbon, nitrogen, oxygen. In the first sentence, the word sinters refers to a process of sintering. Sintering happens when you heat a powder material to a temperature below its melting point, and a new bond are formed between the grains of powder to form one large mass. The most commonly used definition tends to include what the note says. There are several modern ceramics materials which don't actually involve a metal. The syllabus, for example, includes silicon oxide. And there is a past question which tells you that silicon carbide is used in ceramic and asks you to deduct things about it. This is such a huge topic that I will just stick closely to what the syllabus asks. In terms of their giant molecular structure, a giant molecular structure consists of a covalent bonds holding together huge numbers of atoms. If you have been working through a previous statements in section 4, you will have already read about this in learning outcome. The problem is that some of the ceramics mentioned are not covalent. Magnesium oxide is ionic, aluminium oxide is also mainly ionic. They do need to have a giant structure, but they have a giant ionic structure. Other more complex ceramic will contain both ionic and covalent bonds, some of which may be highly polar. The strong bonds holding the atoms together in 3 dimensions will make the ceramic hard and strong, but also brittle. Think about a ceramic wall or floor tile as a simple example. the tile is obviously hard and you can stand on the floor or place heavy furniture on it without it broken. So it is strong on the napping. Hence, it isn't difficult to break a tile in half by snapping it, especially if you score a shallow line on it with the first cutting tool. It is brittle